Our December structural modeling video conference, and we're going to talk a little bit about today about the state of the software project, and also talk a little bit about where we're planning on heading with these software artifacts and the things that are going that the software will help us do. So just to go over the agenda here a little bit, the current activity overview. We've been working on the structural modeling project software, which essentially in this phase, we've taken the George Mason University Interpretive Structural Modeling software interface as it was described in the handbook for interactive management, and we're implementing software that produces the same outcomes, which is kind of interesting because we don't have any open source software for this. We're not quite sure, if we're doing, the same algorithm, but what we're doing is we're trying to reproduce the same behavior. So we've had some success in that, in going through and producing the same behavior and outputs from the software, open source software that we've created. Some confidence that we're kind of on the right track. And what we have is we have basically three kind of flows of the software right now. The first one is the software project, the main software project that's on GitHub, which is one of the projects on GitHub, I should say, is the main development flow that has all of the versions in it. And that's the one we're working on. Now for the Seattle GNU Linux conference, we cut a specific version of the main development tree and put it out in its own repository. Really an example of a manual type of software development where the operator the matrix operations and enforces the algorithm. And then the second, I should say the third software repository out there is SMP Phase 1 software version. Simply automates the matrix adjustment component in the algorithm, in the manual algorithm operation. So that's starting now to go through and to automate the algorithm.
Good morning, Janet.
Good morning. Only 3 minutes to get on this time. Pretty good.
Yeah, it takes time. It takes time. They change the interface a little bit every month.
Yeah, that's innovation.
A little bit at a time. So one of the things that's been interesting to me is I go through and working with the software, and especially the detailed reproduction of the behavior of the GMU ISM software, is the fact that we're not working with a global ISM model that does everything yet. So what we're doing right now is we're working with specific software algorithms that address specific types of natural language structuring relationships. And we've kind of taken and implemented the ideas of the AMEI, the concept of the AMEI, so that we can have a clear logical set of groups by the characteristics of these natural language structuring relationships. But what we found, and to talk about the future activities here, is we not only do we need to talk about these, very specifically talk about these types of logical groups that go with natural language structuring relationships, we also need to talk about the concepts of global and local relationships and what they mean. as well as relationship precision. The AMEI, if you have a natural language relationship that can fit in any one of the 27 logical buckets, that's a very non-specific or non-precise type of relationship. And of course, the example there is connected to. The two is the natural language relationship that was used in the AMEI presentation. So that is an example of a natural language relationship that fits in all 27 categories. There are natural language relationships that only fit in one of the categories. That natural language relationship is much more precise than a natural language relationship that would fit into all 27 buckets. Okay, so those are some of the concepts and some of the language that I think that needs to be developed more precisely as we're going forward. And then another interesting thing about the Handbook of Interactive Management is there's the application structural types. There's a list of about 16 of them in there. And they're really a combination of fundamental approaches, algorithms, and matrices and steps. So the plan is to group those, first of all, into two groups. And we'll call those basically a primary and a compound application structural type. And the primary application structural type, I have a direct relationship to a specific type of mathematical matrix implementation. And there's subordination matrix, implication matrix, priority matrix. Few of those types that map directly the names between the application structural type and a type of matrix. And then other application structural types use more than one type of matrix or one type of approach. So we'll call those compound. Anyway, those are the kind of some of the future things we're looking at. And to make a map between the software commands and the mathematical structural types, or any missing structural types that need to be, any other mathematical types that we need to implement in the software to fully support all of the listed application structural types. And the reason for this, why we're doing this, is kind of to get an idea of what kind of software architecture, what kind of modular software architecture is going to be needed to be applied when we create these primary components, because we know that these primary components, we're going to have to use them in sequence or use them together or somehow have some interfaces, interaction between them to produce the compound structural types. So we want to start looking at that architecture and figure out a way that we can produce software modules that can be integrated to achieve and produce the behavior of these application structural types. So is there any questions so far?
Gosh, yes, probably about 150 or so.
Well, that's a small number.
I don't know, that's a number I just plucked out of the air, but I mean, you've just covered an awful lot there, and I don't know if the screen is meant to be changing, but I still have the agenda on my
Yeah, no,
screen.
I just walked through the agenda. So.
Okay. Okay, so I mean, maybe we should wait for you to proceed, but and maybe this is not germane to this particular session, but you're talking about the 27 logical property types, and I mean, just from a basic point of view, what is interesting to me, and maybe you can point me into this later on, is how the process of mapping the the natural language presentation or the natural language relationship to the one of these 27 different types and the process by which that goes along. And I think this sort of, maybe this, I'm leaping ahead here, but for someone who's relatively, well, I'm not totally new to this, but the intricacies of what you're doing in this project, you know, are such that for someone like myself coming to it, understanding how these relationship properties with their unique identifiers relate to the natural language relationships, that's something that, you know, would be perhaps, you know, well, it would be very helpful.
Okay, that's a good point, Peter, and I think that it's probably something that we've kind of glossed over a little bit. And I'll just take a few minutes right now to try to give a little bit of background on it. Looking at all of the ISM literature, we found that there were a number of applications and different authors and different people who were using more or less colloquial names like subordination matrix, inference matrix, priority matrix, things like that, to mean actually specific types of logical structures. And when you go back and you look at the mathematical of structural modeling or structuring complex systems that Warfield wrote, published at Battelle, he had a restricted set of logical properties. And because the mathematics and the logical piece was published by Battelle and not well known to lots of people, there was a lot of confusion about that. And then that's kind of one of the background pieces that talks about the AMEI and the 27 buckets. Then the other part is that what we really want to do in complexity reduction is we want to reduce uncertainty. When we read the literature and you look at it, it's uncertain what these authors are really talking about. You see different logical properties associated with the matrices that are supposedly the same type. So we decided to create the topology, the 27 buckets, to cover all the different combinations of the logical types. And those are listed in the AMEI. Are you familiar with that, Peter?
Yeah, I've got that. Yes, thank you. And I just think that what I'm looking for someone who may not want to get to the even this level of discussion is a way to take a sentence, if you like,
Yes.
and to go through some exercises to understand its structuring in mathematical terms, or as it relates to one or more of the 27 types that you've identified in the approach that you're taking. And that is it sort of relates to the algorithm flows that you're talking about and we've discussed, is how to make them entirely transparent as you go along in this software development, and also in the manual approach that you were talking about, so that we can step people through it in a logical way, for want of a better term.
Yeah, no, I think that's perfect. That's just perfect. So there's a chart in front of the AMEI which gives some sentences about.
Right, I've been looking at that. Yeah.
And then if you notice at the bottom of that chart, it says it was developed based on a book on, I think, predicate logic.
Yes, exactly. Mm-hmm.
And so that book, then in the appendix in the back,
right,
goes through in detail the type of sentences that you're talking about.
Okay, all right. Well, then I'll take a look at that, because I think it's sort of essential for the work that we're doing on systems literacy, for want of a better definition at the moment, but to be able to step people, anyone, through the rationale for this and the sequencing, if you will, of the process, and so that they can understand how these how this is actually working, and it's not a black box.
Exactly. That's yes.
Which is what your intent is anyway.
Yes, and there's another kind of not well known, but I think a significant aspect, and that is the fact that individuals naturally see things differently. They have different types of relationships. One of the people in the systems engineering community was a software engineer, and he was also a hardware engineer. He had T's in both areas. So he wound up managing large projects that had both software engineers and hardware engineers working for him. And when he was doing his doctorate degree, he was working with graphical languages. And what he noticed is that there's graphical languages that represent relationships, and their software, UML and SML, has a language form of relationship which is different than from IDEF0 and other types of mechanical representations of relationships. So he was intrigued by that because when he took a software representation of a relationship and showed it to his mechanical engineers, they couldn't understand it, and vice versa.
Right,
So
and that's really getting to some of the nub of the engineering challenges that are faced today in education across the board. And if we're not able to create the avenues to that cross understanding or trans understanding, well, that's the goal that I think, one of the goals that we're after. And this,
just to add another phrasing to that, Peter and Dwayne and Michael and I are seeing more and more that people in model-based systems engineering are talking about the need for a more coherent understanding of modeling in all of its forms. So that goes along with this work, that people have been satisfied with one or two approaches that they have learned according to certain conventions, and now they're finding, after all the years that Incosia has been pushing for model-based systems engineering, that they really need a broader and deeper understanding. So this is, echoes what Peter's saying and what you two are doing.
Well, that's very interesting, Janet. I think I think it was at CSER, some of the early ones. I think back in New Jersey, we had when the first UML push was on. There was some other people there that worked for some governmental agencies that gave a similar type of talk about the confusion between relationships and how things work. And what they did was they were mandated, on one hand, from their technical people, that they had to use UML. And on the other hand, specifically, this senior analyst, and I went into the director's office. I started talking to him, and the director stood up and says, "Get out of my office until you can come back here and talk to me in English. It's something I can understand." And so they went back and they did concept maps. They looked at Novak's concept maps, did some of that, and did a transform between them. The difference between UML, SysML, and IDEF0 is those are all equivalent forms that you can logically, I mean, you can compute those. Those are formal languages, so you can make direct translations between them. The part that's missing, I believe, a general part is understanding that people fundamentally see things differently, and that because they see them differently, we need to really have tests for the individual. And so if you have some type of test that says, oh, this is the way this person sees things, then you know how to present the information to them in the way they see it.
Right.
And
Donna Rhodes of MIT is going to give a talk on Wednesday, a CERC talk, on the human element in model-based systems engineering, which is exactly what you just were talking about there. It's good that this is finally getting really focused attention. I think there's a lot of work that needs to be done, but it's the key missing element.
that's the very,
I can send you the, I don't know if you've seen that CERC talk. I'll send you
I've seen that. I've seen that. It's I think that there's a lot of these areas that need to be kind of and have strong interfaces. For example, testing. If I have 50 hardware engineers and I have 100 software engineers, testing them to see, how they view things is not going to provide any value unless I have an infrastructure that allows me to adapt to that. And to adapt, to have that infrastructure that allows our models to adapt and present to an individual the way they naturally see things means, first of all, I have to be able to translate between the models, understand how those model translations are integrated at the higher level. So you're really doing multiple model integrations. And we have seen, in my experience, and kind of what I'm seeing now, is there's essentially just groups that go and say, well, you have to understand my model. You have to understand what I do, because this is the way we do it. It's mandated this way. And until we start finding out that you really need to be able to understand the human differences in perception. And I think the one thing that was really interesting about the fellow that was a hardware and software manager, he said basically he believed in the final analysis the reason these people became hardware engineers, or the reason these people became software engineers, because that's fundamentally the way they're comfortable seeing the world. And I thought that was kind of enlightening. So anyway, that's kind of a track down the other side, but it's kind of where we're going with this. And so there's a lot of work that have to be done by psychologists. There's a lot of work, people that have to do with people about perception and figuring out tests and so forth that really is not associated directly with what we're doing here, but it's a very strong interface. Okay, so let's see. That part, let's look over here. And I'll take a look, go through and just walk through the read ahead a little bit. I'm going to change this out. So application window, read ahead here. We go. So we should have the read ahead up now.
It's there.
Okay. So this basically.
I've got the agenda still.
Okay. Well, let's see. Maybe it takes a little bit of time for it to get there.
Mine came unusually fast.
Well, that's because we're on the same level. So you got the read ahead yet? Well, I'll kind of walk through it while we're waiting here. I sent it out earlier too, so if it doesn't show up, you should have a copy. But
Janet?
I'll go find that.
So basically, the thing that was very interesting in the last month, where we found out the work that Michael Hogan was doing at the University of Ireland, Galway, psychologist, and he's focused on freedom, and he's focused on effectively dealing with complex situations. And they're using Warfield's Societal Systems book as a antidote to talk about the massive amounts of data overload and the way that we're actually using our technology to overwhelm ourselves and not really get any make any progress with answers, basically, in large-scale social systems. So he points back to that book. He has a blog on Psychology Today, talks about that. So I was really interested to run across that specific set of work. And it matches very closely to the outcome basis that we want to see. We want to be able to support large group problem solving with these types of softwares and these types of techniques. So one of the key things about that, and I think there's also key things that Kevin was talking about, is the fact that the software is closed source. And so the software really has to be open source for people to even understand it. And it's becoming more clear to me that one of the problems with the implementation of these techniques has been the fact that the software was closed source. Because nobody understands the software is a mandatory component to deal with the complexity, and if it's closed source, nobody can really understand what's going on. So, given that specific approach, I gave a presentation that we gave a presentation, Kevin and Thomas and I, at the Seattle GNU Linux conference, and they're very interested in freedom and supporting not only technical freedom but also political freedom. And it's got some fairly interesting responses there. So the software itself had cut a version for the Seattle conference, and I also cut a version for phase 1, which is automated matrix scanning and row and column swapping support, so that's out there. And the phase 2 that's in work is the automatic algorithm execution. And then phase 3, which we need to do, is the add group network support, editing, process control. These are all the types of things I think we were talking about this morning, which get large groups of people in the proper attitude to deal with large-scale social systems. So the phase 1 is complete, essentially with a augmented manual approach to doing the GNU-ISM software 3 commands. The key part here, though, is that we are implementing specialty types of algorithm. We haven't developed a global algorithm that will do them all. And as I start looking at this specific idea of one algorithm that would kind of solve any kind of interpretive structural modeling approach, I'm wondering if there is one. And so it's going to be interesting to look at that. Is another key part, because of the closed source software, the poorly defined topology of the logical spaces, that maybe we had different types of global approaches that didn't quite solve everything, because that might be very difficult to do. So that has been enlightening as I've been going through and creating this particular set of work. But anyway, the phase 1 is available and it's out there. And as I talked about, the general algorithm itself, we haven't developed one, but the general algorithm the example that was used to display or showcase the do model in the handbook is a very simple asymmetric ordering natural language relationship, which really only fits in one bucket. So when you have natural language relationships that are very precise and fit in only one of the 27 buckets in the AMEI, then we can focus our software algorithms on that logic. But if you have something that's much more general, like is connected to, which hits all 27 buckets, if I'm thinking about a software implementation that will do that, that's much more challenging. And so what happened is, in the do model, they used a very simple, very precise natural language relationship to present it and to give an example of it. And so there really is, not a general example of a complex situation that's to test the do model, it will do everything. And so that kind of leaves it up in the air. We really need to kind of find one of those. We're looking for one of those. I think I have a couple of candidates out of some of the published literature, and the next one or two meetings, I'll pull one out for discussion. But I think with the identification of the general algorithm test case is important, and we need to really probably have one or more, people to discuss what that means. Okay, so now we have the group process design. And I think this goes back a little bit to what Peter was talking about earlier. That is actually how to start implementing and using this approach in the software. And the Michael Hogan provided a copy of the software that they use, which he calls collaborative intelligence. I think that's some of the work that was done by Arizona, to the person's name, but anyway, it's kind of one version of software. Kevin and those people have the Cognoscope version. All these different versions, but we're not sure how the algorithms work.
I think I've got that somewhere, because I attended a training program at the National University of Ireland in Galway last year.
Oh, good.
As part of an EU project that I'm participating in called it's a Horizon 2020 award called Sea Change. And Christine Donegan, who is a professor at the university, ran a week-long course on social innovation and participation. They called it SIPS, participation planning. And part of that was, a group process that uses that ISM software. And so I presume that she and Mr. Hogan, or Dr. Hogan, Professor Hogan, are working together. The question I have is on the work of Michael Hogan. Have you posted that on your website, or is it available to us to look at somehow?
Well, yeah, I've posted it on the website. It's also in the
reader head, is it?
No, in the presentation I did for the Seattle GNU Linux conference.
Oh, okay. I'll go
It's
look
in
for
those
that.
charts, and can't find it there. I can definitely send it to you.
Okay, I'll look for it. Thank you.
Yeah. But anyway, so that's the group process design. There are different people that have different kinds of processes, and again, the software is mandatory. Software is closed source right now, so it's not really sure how the software algorithms impact the group decision making, because if each different piece of software is different, then you're going to have
Right, exactly.
differently. So what we're looking at is, okay, now we have open source software. Now we need to understand how that's going to impact the group design. So, and then the effective individual engagement, basically just need to figure out what people are interested in doing and how we can cooperate and coordinate to get things done.
Yeah, how can we contribute to that? How is the best way? Is that to assemble a group of people? And is there like a minimum number you think that would define a group, or a maximum number that would define a group, in order to look at that? And are there some outline guidelines that you might give us to help with that process?
Well, Peter, I was hoping that Kevin would be here on the call, but I consider Kevin the absolute expert in that area. And
Okay.
and I'll put it in the notes and I'll ask him that question. He's had a lot of experience in doing this, working with groups, group facilitation. He understands the pitfalls of a number of different things. So I think that working with Kevin on that, I think would be probably the best way to go.
Because I'm also looking at how, there's obviously a number of different processes that groups can involve in to reach decisions. And one of the ones that I'm working with is Colin Eden and Fran Ackerman's work on dialogue mapping, if you will. And I'm just wondering how one might support the other in some way. Their approach, you have sort of green and red dots, and it's sort of more to move along in assigning priorities. But it would seem to me that some of the ways that they suggest eliciting ideas could be helpful, and then how we structure them could be a part of.
Right. So the green and red dots really are mapped over a yellow field. And so the eliciting of the knowledge from the group so far is kind of hidden from, or, from the process that you see of taking a field of yellow unknowns and mapping them to a field of knowns.
Exactly.
What we're trying to do with this is there's many different ways that can be done, but what we're looking for is an efficient way. What we really want to do is we want to try to figure out the maximum use of inference that we can to actually get the ideas in as efficiently as possible. And so there's a structured type of approach, and these things that you're talking about are kind of assumed have already been happened, and then we'll go into the mathematics, but that is why I've talked about the group design, the software design, and that process, because that interface needs to be developed.
Yeah, but in your read ahead here, you're saying that they're separated. That the algorithm approach and the group process design are two separate processes, and I'm wondering if to the extent that the interrelation of that is of consequence, or why you've made the statement that they're separate processes entirely. I mean.
Yes, so what we have is essentially we can have a algorithm development, the algorithm design activities. When we get to the group design, the group is going to work with one specific algorithm. And so the group, or the person that's designing the group process, will be presented with a menu pick list of algorithms to use or processes to use.
Okay.
The algorithm will be associated with those. Designing the algorithms it has to happen before you can have that menu pick list. And what's going on right now basically is designing these algorithms, the ones we've done so far, are really not based directly on the algorithms that the mathematics of the algorithms within Warfield's published work. What they're based on is the behavior of the software. When we look at the behavior, the way the software behaves, what I was able to discern from that was basically some very standard computer science algorithms seem to be employed. And so what I'm doing now is I'm taking these standard computer science algorithms and saying, oh, okay, well, if we did this and we applied it, used this algorithm, like binary search or simple search or compound type of dual array search, if we did that, then this is the outcome we get, because we really don't know what the algorithm is. And so that's really those types of implementations, the specific code that we're writing is based on how we see the ISM software is documented to behave, and then map that to computer science algorithms.
Okay.
And I think when we go and we look at it, we say, well, now what we got to do is make a general, a algorithm that will cover them all. I'm not familiar with a basic computer science algorithm that will do that. And then to do that one, we're going to have to go back to the drawing board. So when I'm talking about the algorithm design activities, those are the types of things I'm talking about.
Okay, thank you.
Yeah. Okay. Well, let's see. Now the current considerations, we talked about the art and the M, the I, how we're doing the buckets. There's the idea of local and global. And I think this is another concept that needs to be put together and discussed in a little more detail. But the types of relationships that are used, like with Cognoscope and some of the other software pieces, are very local. It's like influence. Influence, it really, is an operation between two objects. Whereas the do model was the natural language relationship that was used there to demonstrate the global model is heavier than. Well, is heavier than, of course, is a global type of relationship. It's really not dependent on the interaction between the two objects. And so you rate and rank all the objects based on their weight. And so that is really a global type of relationship that has a single thread through the graph. Type of relationships like influence, it could have multiple threads through the graph, could be disconnected. It gives you much more variability. And so we'll be working up and and further developing these concepts and show how they impact the structured graphics and the mathematics. Okay. Pretty much that part. So now let's go and look at some of the software we have.
For whatever reason, my screen is still not refreshed. I've been going along on the talk ahead. I don't know if Janet's has refreshed.
Okay.
Oh, that changed something. You did something there.
Okay, let's see if we can try. Let's try this. See how this works.
All right. See your face now.
Okay. Whoops. That's not the one I want.
Oh, that's changed.
Okay, so I don't have the one I want. So I'm going to go back Say okay. Went to our application window. Okay, I want to show this one. Okay. All right, now should
I
be
see your
able,
desktop. Yeah.
well. Let's start over. Application window. Okay, present to everyone. Okay, it should be the clusters of equivalent objects up there.
I see clusters of equivalent objects integrated application. Yep.
Okay, so this is the clustering command out of the GNU ISM software. I'm going to just run through it real quick. I have an automated that tests the interfaces, and I have that specific set of commands programmed. So I'm going to run it real quick, and we'll go back through and we'll talk about it a little bit in a little slower, a little more detail. But once I'm just going to go through it kind of real fast. And so what this does is the user no longer gets to implement. The user only gets to say yes or no. So when we were designing the algorithms, we did a process where the user, the operator, actually input those numbers, object 1, 10, 2, 3, things like that. Now those objects and those object numbers are being selected by the algorithm in the background. And the user can only say, okay, yes or no to each question. So the object, so you can see that the object numbers are changing. And you're asking if they're in the same class as, or if they're equivalent. And if they are equivalent, then they're clustered into the equivalence classes and placed in vectors below the main matrix. When it's complete, it's done. So that's an example. And one of the things about the recording process is it doesn't show the buttons being clicked. The buttons being clicked when you're actually, let's see, let's change this. Say it's in matrix size 8. And let's say, are they the same class? Say no. So when you're actually doing it on the screen, you can see the color change, but when it's recorded, it doesn't, when it plays back, you don't see that. So you can see, you can just cycle through this and say, okay, these are all individual things. None of them are the same as the other. Or if we go like, let's go with 9, we say, well, yep, these are all the same thing. They're all the same kind of thing.
I can just tell you,
I mean,
my
everything
screen's
will
not
be
changing, so
Uh-oh. Is that the same with you, Janet? Your screen's not changing?
My screen is changing.
Okay. Well, that's
okay, never mind then. I don't know why that would be.
well. This will be recorded, and it's out on.
Well, it takes longer for the electrons to get over to where you are.
That's right. Might have some filters that's going through. Put it that way. Okay. So that's basically that particular command. I'm working on the other ones. They're a little more interesting for a couple of reasons that I've already explained earlier. But so that's that one. I did eliminate the preview I did of this where the audio didn't record, and the audio itself I'll probably do a few short videos once this is kind of more complete. Or I might just do one for the cluster and then do one for the one only or more than one. We'll see how that works out. Okay. See, we have about 10 minutes left. Is there anything anybody would like to discuss?
Getting back to the question of the relationship between the group modeling and the algorithm design. One of the big issues, I don't know if we want to talk about this some more, is there's the need to map the natural language to the logical type in order to get it into the algorithm. But there's also the local versus global is at least as thorny. Maybe you want to say some things about that, because in order to get in your algorithm, you want to deal with global relationships across objects, right?
Well, the global attribute or the global characteristic of a natural language relationship generates a single thread through the graph, a single structural thread. And when we have that single structural thread, then we have a lot of advantages for inference, and also a lot of advantages just for the logical understanding of what's going on. We have the local one, where we could have multiple threads that intersect, multiple groups and so forth.
Could you revisit then how you're using?
Hello, Janet. I didn't get all of that. Well, I think Janet dropped out there for a minute. But
yeah, I'm having a little trouble with the connection. I don't know if you can hear me.
I can just hear parts. I can just hear parts. But let me kind of talk about the local and the global a little bit. And as I pointed out in our the graphic that we showed in the read ahead was from one of our papers, where we talked about these types of relationships, and those types of relationships were detailed fairly clearly by Warfield and Christakis in a couple of their papers. They didn't go into logical detail, but they did say that there were these types of relationship attributes, and then you just kind of left it at that. Those relationship attributes impact the type of application structural, and that's one of the 16 types we talked about earlier. So Mary and I were thinking about just developing a chart, and hopefully we'll get that chart going and start filling in some of these attributes and start making a more structured view of the application types, and hopefully that'll help. But it's a key aspect. So the local attribute on the structuring relationship is the more difficult one to look at. And when you think about the binary matrices and the way that in that paper in binary matrices that Warfield wrote, where he actually took a local type of relationship and separated it, where you could then take it and make it into a local relationship with clusters of global relationships. And so one of the primary things that it appears you need to do is to be able to identify the structure itself, look at a local relationship and say, oh, is there any inherent global thread in here? And if there is, then we'll run our processes on it, pull out the global thread, and then address the local or network components separately, one at a time. So that's kind of the approach.
As I recall last week or last month, Kevin asked whether these notions of this treatment of local and global were yours, or whether they'd come from elsewhere. Was that, am I correct on that?
Yeah, so he, I think he did, but so what we did, is in our entropy metrics, our entropy metrics paper, Mary and I developed this idea of global and local so that we could talk about the components that are in the representations of entropic systems as developed by Hitchens. So Hitchens kind of talked about, oh, this is the way you could view system entropy in a way. And then what we did was we added, Hitchens did, and we added information entropy together. And then when we brought the Hitchens type of system entropy and information entropy together, it became clear that these local and global types of relationships were a key factor that allowed you to make decisions and reduce uncertainty and reduce complexity within these representations. So we've published that in a couple of papers already. And if you're interested, I could send you the copies.
Okay, no, I'm looking them up right now. Thanks.
Okay.
Yeah, so I wouldn't mind seeing them somewhere, actually. It'd be good, or I can look them up somehow too. If it's easy to send them, that would be easier.
Yeah, I can send pointers to the, yeah, I'll just send, I'll send you copies of them. You can look at those. Yeah, so it's the, so the local and global in the context work together to reduce uncertainty and reduce complexity.
And I think how one then takes the group process to bring that forth is an important part of the puzzle.
Very, very, because this can be extremely clear to certain people and probably completely opaque to everyone else. So you've got to understand that, and then once you understand that, you have to figure out, well, what are the transforms that each different kind of person would need to look at it. That's a key aspect of isomorphism, because you have mathematics, graphics, and prose, and they're isomorphic. So some people understand the prose, some understand the graphics, some understand the mathematics.
Well, then you've got the whole cognitive processing capability of the individual in question as well. I mean, their whole emotional cognitive makeup.
There you go. All those different factors. Well, we're down to the end of this session. I have some papers to send out. Is there anything else? Okay.
Thank you very much.
You're very welcome. Thanks. We'll try it again next month. See how things are going. Okay, Janet.
You too.
Happy
Bye-bye.
holidays.